Thank you very much for the introduction. It's very good to be here. I'm a professor of engineering design at Bristol University, and I actually have a research grant to research the understanding of biological systems using engineering principles. So the things I present in my creation talks are based on the research I do at my university. And one of the things I found, my testimony, is everything I discover from practical science and experiments supports what the Bible teaches about creation. I want to explain some of that this evening on this particular topic, the wonder of the nervous system. What I'm going to present tonight is in a book that I've written called The Wonders of Creation. And one of the reasons for writing this book, The Wonders of Creation, was to give credit to the Creator, as it says in Psalm 29, giving unto the Lord the glory due his name. And the reason I was so keen and passionate to do that is because of, well, the BBC and natural history programs that really give an atheistic worldview. Perhaps you've seen Life on Earth or The Blue Planet or The Wonders of the Universe. And one of the features of those programs is that God is not mentioned at all, and there's no credit or glory given to God. If some of the past scientists were here today, like Isaac Newton or Lord Kelvin or Michael Faraday, they would be amazed that people could talk about the wonders of the natural world without any reference to the Creator. So that's what I wanted to do, writing that book, which I, by the way, co-authored with Andy McIntosh. And it's not just that these natural history programs do not mention God, but also they give very confused teaching about some of the aspects of the natural world. Just to give you one example, in the Blue Planet 2 series, this is what David Attenborough said about life in the oceans. He said, "We might have expected the deep sea to be truly barren, but there is unimaginable abundance. Astonishingly, there is more life in the deep sea than anywhere else on Earth." So he was really, really surprised. The reason he was surprised is that it's very cold in the deep sea. There's very little light. There's really high pressure. There's little food. So with his atheistic worldview that comes across on the BBC, they didn't expect to find very much at all in the sea. So they were astonished that, and it is astonishing, more life in the deep sea than anywhere else on Earth. This was only discovered just a few years ago when they sent down the submarines. But if David Attenborough had just read the first page of the Bible, the first page of the book of Genesis, this is what he would have read: "Let the waters abound with an abundance of living creatures." So the Bible tells us that we should expect to see abundant life in the seas, because that is what God commanded. And when God commands something, then it happens. And it's wonderful in that verse. Notice how it says, abound with an abundance. So it's really emphasizing it's God's character to create in abundance. Whether you're looking at stars in the universe, or fish in the sea, or flowers in the land, God creates in abundance. It's exactly what you'd expect from a creator. So it's sad that we have these natural history programs where David Attenborough says things like that, which are contrary to the very character of God. The reason we called our book The Wonders of Creation was because in the book of Job, he often mentions the wonders of God's creation. And there's a particular verse here I really like where it says, "God does great things past finding out, yes, wonders without number." Whichever part of creation you study, that is indeed what you find, wonders without number. Our book was published fairly recently, but it's already been translated into one other language, which is actually American. We thought they would just sell the English copy in America, but they actually wanted to translate the entire book. Not just the spelling, but some of the punctuation and sentencing as well. But I recommend the Queen's English on the left. So in this talk, I just focus on one particular aspect of design. That's the wonder of the human nervous system. I think this is one of the most spectacular examples of design and evidence of intelligent design in creation. It's a subject very close to my own heart because I've worked for the European Space Agency and particularly worked on 4 different Earth observation satellites, and I had to do a lot of the wiring on those satellites. I was responsible for designing the deployment system of the solar array. This is the last spacecraft that my solar array technology was used on. The METOPS-E, a meteorological satellite launched in 2018. And I had to design the wiring for particularly the power lines coming off of the solar panels. The solar panels were about the size of a badminton court, and I had to get over 300 wires down a robotic arm and onto the spacecraft, and that added up to about 30 kilometers of wiring. Now on a spacecraft, that represents the pinnacle of man-made technology. So I was really fascinated to compare the wiring in the human body. That's the nervous system, is basically a wiring system. I wanted to compare that and compare it with the best of man-made technology in a spacecraft. I thought this would be a wonderful comparison, particularly with my own experience and with my grant to actually do this kind of study. So with a spacecraft, the wiring system is the system that needs the most design and planning, because the wires integrate everything, the power systems, the instruments, the solar panels. Wires do all the integration. That's why it needs such intricate design. The wires go round in precise bundles. I don't know what your computer at home looks like. If you look behind it, there are probably wires going all over the place. Well, on a spacecraft, you can't just have jumbles of wires, so all the wiring has to be done very precisely in the right bundles. The wires have to cross moving joints. On a spacecraft, you always have rotating antenna or rotating solar panels or other pieces of equipment, and the wires have to cope with those movements. That's another challenge for someone who does the wiring. Then the wires also have to pass through structures. And it's one of the challenges for a wiring designer. I had to go and meet up with the chief structural engineer for the spacecraft, and I had to say, I'd like to put my wire right through your structural beam. And he said, he would say to me, well, I would like you not to do that. And I said, well, I'm going to do that because I'm the wiring engineer and I have the final say on all these things. And I would have to put my wires through other parts of the spacecraft, the thermal parts and instrument parts. The wires had to connect and integrate everything. And so of all the different parts of a spacecraft, the wiring is the most challenging and needs the most planning. Actually, this just a few pictures of bits of the spacecraft I have personally designed. When I look at that, I remember those wires. You can, on the left-hand side, the red wires, they're the 300 wires coming off of the solar panels back down to the spacecraft. And on the hinges, they're covered with Kapton and silver foil, a kind of thermal blanket, and then they're bundled and they go through connectors. So I've been doing this for the European Space Agency for 20 years, and so I thought, well, it'll be fascinating to compare this with wiring in the human body, and it's been a really fascinating study that I've done. So just to introduce this, a few pictures of sports people. When you watch these sports people, you probably think, I wonder who's going to win this competition. But since I've been working on this project, I now see things in a different way. I look at these sportsmen and I think, how can their brain react so fast, and how can they move their arms so fast? What's going on in their nervous system? So it's got me looking at life in a very different way now. Again, by way of introduction, just to show you a couple of things that a human body can do, and probably you can do. One of them is humans have an amazing ability for a delicate touch, delicate control. It's one of the things that's uniquely human about us. On the one hand, we can pick up a very heavy object, probably around 20 kilograms. Most of us could pick up a heavy object. But on the other hand, humans are very good at picking up a very tiny, delicate object. So we can pick up a grain of sand weighing a tiny fraction of 1 gram. So not only are we strong, but we can be very delicate as well. And the reason for that is that we have 650 muscles in our body, but each muscle is made up of several muscle fibers. And if we want, we can activate just 1 or 2 fibers to create a very delicate force or a very delicate pinch. In fact, there's a part of the brain called the motor cortex that drives our muscles, and our motor cortex is able to fire a single neuron in order to fire just a single muscle fiber to give a very delicate force. That's not what you would expect by evolution, but it is what you would expect from a creator God who wanted us to have very fine skill. But as well as being able to control our muscles, we also have fine sensing as well. Humans have an incredible sense of touch, so sensitive that we can sense when a tiny fly lands on our skin. Amazingly, our brain is receiving over 1 million signals a second from millions of sensors around the body. But the human brain has this incredible ability to filter out of those millions of signals. It can tell us which 1 or 2 are interesting to us. So your brain receives 1 million signals a second, and it can say, hang on, a fly just landed on your middle finger of your right hand. And scientists are just stunned that our brain can do that, and they don't understand how it can do that. And it is an amazing thing that we can detect a fly landing on our skin, a fly weighing a fraction of a gram. So how is that possible? Well, one of the reasons it's possible to sense a tiny insect on a hand is that when it lands on a hand, it will touch a hair, a single hair, because on the back of your hand you have those little hairs. And if you look on this screen, if you look at the hair shown on the right-hand side of the diagram on the left, when the hair is just deflected by a tiny amount, look at what is at the bottom of the hair. If you look at the bottom of the hair, you'll see it has attached to it several nerve fibers. So when your hair is deflected by just a millimeter, those nervous sensors your nervous system can detect the tiniest of movements. And then a signal goes up through your body, through your hand, through your body, up to the sensory cortex, the part of your brain that receives signals from the millions of sensors around your body. And not only does it sense that something deflected a hair, but it knows which part of your body that happened on. It's the most incredible ability. So I'm going to give you an overview of how the nervous system is designed, how you can do those incredible things. And as I go through it, you'll notice blue normally is for the it's just a code for the signals going up to the brain, and red I use for signals coming down. That's signals to drive the muscles. So in your spinal cord, you have signals going up and you have signals going down, sensor signals going up, motor signals going down. So I'm going to just tell you briefly 10 really interesting, amazing things about your nervous system. The first thing is it's really well integrated with the vertebral column. The vertebral column is a lovely design of backbone, like cups fitting on each other. And the human back is a wonderful design. Obviously, it's not nice. If you have a disease or an accident, then you have a painful back. But if you, aside from disease and accident, the back is a wonderfully good design. At Southampton University, they have a big grant to study the human spine in order to be inspired to make better bridges, because engineers see the human back as a wonderful design. Not only is it a very strong structure, but it has a wonderful integration with the spinal cord, because there's a hole right down the middle, the vertebral column, and then there are these slots at the side for the nerves to come out. It's a brilliant design. It protects the spinal cord. It gives it very strong protection. And there are 31 pairs of spinal nerves that come away from the vertebral column. So that's 62 nerves in total, 31 pairs. And I'll show you some pictures of what one of those nerves does as it comes out. Sorry. So secondly, all of the signals from the brain have to be funneled into the spinal cord, which is only a couple of centimeters in diameter. When I was studying this, I was thinking to myself, I had to do that with wires on the spacecraft, but I was only dealing with a few hundred wires. In here, there are hundreds of thousands of neural pathways, and they are funneled into a tiny spinal cord. It's the most incredible design that it could all be funneled into that narrow spinal cord. And at this point, the signals are kept separate, so you have a separation of the sensory signals, the ones going up, and the motor signals, which are the ones coming down. Then what you find is that, so this is now showing one spinal nerve coming away from the spinal cord. As I said earlier, there are 31 pairs of these nerves. This is now showing you what one spinal nerve looks like. What you notice is that one spinal nerve is made up of several smaller bundles of nerves. And when I saw that, I thought, wow, that's so similar to what engineers do. You can see an engineering cable on the left with a sheath and then lots of mini bundles, and that's exactly what comes out of the spinal cord. And it's the kind of thing that has to be planned and designed. It doesn't just happen by chance. But in fact, it's more impressive than that, because what actually comes from the spinal cord are two sets of bundles. There's a set of bundles, the red ones, the muscle nerve bundles, but there's another set on the other side of the spinal cord, which are the sensor nerve bundles. So you don't have just one set of bundles, you have two sets of bundles to make up a nerve, because in any given nerve, you need both sensors and motor signals. So it's remarkable how they come off separately on the spinal cord, but then they're grouped together. And again, this is what we do on a spacecraft, but it has to be designed. It could not just come about by chance. So this picture is showing you a little bit more of a real life picture of how it looks. So you have, this is showing two pairs of spinal nerves, two on the right, two on the left, and for each case it's showing the motor and the sensor bundles all being bundled together into one big nerve. And as I say, that has to be planned. But then a really remarkable thing happens, because in each of your nerves throughout your body, what you need is a mixture, a mixing up of motor nerves and sensor nerves. Now, in the previous picture, they're still separated. You have individual motor bundles and you have individual sensor bundles. So how do they all get mixed? Well, I was astonished when I saw this in anatomy books. What happens is, near the spinal cord, you have the separate bundles of motor nerves and sensory nerves, but over a short distance of 2 or 3 centimeters, all the nerves become really mixed up so that they're not separated anymore, but completely mixed, which is just the most incredible thing. Over a few centimeters, you have this mixing. I can hardly comprehend how that is possible. That's something that we never did on a spacecraft because it's just too difficult to do. But this is ideal for the human body because it means each nerve branch, because your body is full of branches of nerves, you have both motor nerve pathways and sensory nerve pathways. But again, this feature must be planned and designed. It cannot happen by chance. So this is now comparing on the right hand side an engineering bundle, cables, and on the left side is a nerve from the human body. And it has an outer sheath, and then it has bundles within bundles, again with sheaths. And when I saw this, I thought, this is remarkable. I'm really reminded of those little precision bundles that we made on a spacecraft, except the ones in our body are more intricate and more refined. Then we have nerve branching, because nerves reach every nook and cranny of your body, every millimeter, every cubic millimeter of your body. You'll find a nerve ending. If you get a pin, or if I was to prick any part of your skin over your body, you're going to feel something because your nerves extend everywhere. But how can they do that? The reason they can do that is because the nervous system goes through this incredible branching to reach every part of the body. I can't draw this to do justice to how it's done. But the branching just goes everywhere. And if you just look at that tiny section of skin, just notice how in 1 cubic millimeter, you have lots of these nerve pathways going to little sensors, pressure sensors, temperature sensors, pain sensors, different kinds of pressure sensors, and little, and also the nerve endings going to the hairs, so you notice if that fly is landing on your skin. And so you have these nerve pathways going all over your body, so much so that it adds up to the most colossal quantity of wiring in your body. I mentioned earlier that a spacecraft has, well, the one I worked on had over 30 kilometers of wiring, which to me seemed like a gigantic amount. It took me years to wire up everything. Well, in the human body, if you're an adult, you have around 150,000 kilometers of wiring, vastly more than the biggest spacecraft, the most advanced man-made technology that we do. So that just puts things in perspective. But I'll show you a few other really interesting features of the nervous system. One fascinating one, which really surprised me, is nerve networking. I was assuming that out of each vertebral disc, vertebrae, you would just have one set of nerves coming out. But what this diagram is showing here is that the nerves link up with adjacent nerves, even a nerve, 2 nerves away. So rather than just coming out and staying individually, they link up with each other, and it's called nerve networking. And it's a really clever design feature, because what it means is if you injure one of your nerves, it means that you can still get functioning from your muscles. So if you severed a nerve in your arm, at first you might find you can't move certain parts of your arm, but because of this networking, the nerves can find another way back to the spinal cord. So your peripheral nervous system, outside of the central nervous system, your peripheral nervous system is a very robust design. It can tolerate injury because of this very clever feature. But the important thing to note about this clever feature is that needs planning. You can't just have nerves appearing by chance and then just happening to integrate with other nerves in other places in the most precise way. This has to be planned right from the beginning. Then it's fascinating to see integration with bone structures. When I looked at this, I was reminded of how I had to put wires through beams on a spacecraft, and here you can see in the human body wires going through the pelvic bone. Notice how this nerve, which is the biggest nerve in your body, the sciatic nerve, notice how it's made up of nerves coming from several parts of the spinal cord, but they're linked together. So you just have one big nerve. It's very good to have one big nerve because it gets across the joints in your leg. But notice how it goes through the bone. And that kind of feature has to be planned from the beginning. You can't just evolve bottom up. All has to be designed from the top down. I wouldn't recommend you to try this particular maneuver, but if you were able to do this kind of maneuver, you can be confident that your nerves will not break, but your nerves are flexible enough and they're positioned so precisely that the nerves can last a lifetime and still work. So if you look at the nerves in the arm, it's located in such a way that it can cross all the joints without tightening up, without fatiguing. It's so easy to take the human body for granted, but inside are the most astoundingly sophisticated aspects of design. To me, this is one of the most amazing things about the nervous system, and it's the way it's integrated with all the muscles in the body. So the body is covered in muscles, as you can see on the right-hand side. We have something like 650 muscles, but each muscle is made up of many muscle fibers. So we have tens of thousands of muscle fibers in the body. So if you look at the muscle on the left, there's one muscle on the left-hand side, but notice how it's made up of lots of individual muscle fibers. And notice how each individual fiber, because one's coming out of the picture, each individual fiber is activated by its own individual nerve. So there are lots of nerves getting into each muscle. Now, just try to get your head around this. You have 650 muscles in your body. Each one has many, perhaps hundreds of muscle fibers. Each one of those is connected with a nerve pathway. This is the question, how do those nerves get in every single muscle and every single muscle fiber? How do they get inside? Where are they coming from? It's really hard to picture how those nerves get in. And when you think about it, it's astounding that the nervous system is so integrated with every single part of the muscle system. The nerves find their way into every single muscle fiber in your body. It's almost impossible to draw a picture of how that could happen. It's an incredible integration. And so far I've mentioned nerve pathways driving muscles, but also the nerves also have to control all the organs of the body, the heart, the liver, the kidney, stomach, all these other things. And one thing to note about the nervous system driving the organs is that in many cases it's automatic control. In the case of muscles, it's almost entirely voluntary control, but with our organs, there's a lot of automatic control. So after eating, our brain will control the muscles for our digestion, and we don't do that consciously, it's done automatically. The brain will move those muscles, and that takes a very clever design to do that automatically. Now I want to deal with a couple of objections, because if you read a book by Richard Dawkins or other atheists, they will give these objections. So for example, Richard Dawkins has claimed that the eye is wired backwards. Why has he said that? Well, he says this, light has to go through the eye, and because the light sensitive cells are at the back of the retina, light has to go through the retina to get to the back. And if it goes through the retina, then surely the light is degraded. So isn't that the wrong way around? Now, when Dawkins claims that, it's a very dangerous thing to claim. Firstly, the eye works perfectly well. And if something works well, it's a dangerous thing to claim that it's a bad design just because it doesn't look right to you. Secondly, as I've just explained, the nervous system is the most astoundingly complex, amazing design. And considering what we've just heard, again, it's dangerous to quickly look at the eye and say, I think that's a bad design, I think it's wired backwards. And thirdly, Richard Dawkins doesn't really know of any better way of designing the eye. And also, it's impossible for any of us to fully comprehend how the eye works because it's such an astounding design. So it's a very dangerous thing to make that claim that the eye is wired backwards. In fact, scientists have discovered that the retina has a wonderful design feature, that it has effectively fiber optic cables that guide light through the retina. So light is not degraded through the retina as Dawkins thought. Dawkins' books, by the way, still contain this big error in his argument that light is not degraded through the retina. What he calls a bad design is actually a brilliant design with these fiber optic cables. They're called Muller cells. Your retina's full of these amazing cables that guide light through. It's an example of an atheist like Dawkins just not having the humility to think he doesn't actually understand how the system works. It's more that he's hoping it's a bad design because then that would support his theory. Just to give one other example, Dawkins and many other atheists, one of the first examples they claim of bad design is the recurrent laryngeal nerve. So the larynx is shown in blue, and there's one nerve that goes straight from the brain to the larynx, that's shown in red. But in purple, you can see a nerve that loops down and comes back up to the larynx. Now, Dawkins looks at that looping nerve, the recurrent laryngeal nerve, and he draws a very quick conclusion and says, oh, that doesn't quite look right to me, so I think that's a bad design. But again, he's making the mistake that the design works perfectly well, so you can't just say something's bad if it works well. Again, he's not thinking the nervous system is the most incredible design. You have to be very cautious about criticizing it. And he doesn't understand how the wiring system works either. This subject is very close to my heart, literally, because it goes down there. But I had to design loops on my spacecraft, and the loops I designed were almost identical in size to the human laryngeal nerve. In fact, if Richard Dawkins had come to my first design lecture, he would hear me say that wiring systems normally have loops. It's exactly what you'd expect in a wiring system, but he's never wired anything, so he doesn't understand that. But his books have these catastrophic errors of saying loops are bad when actually loops are good. One of the reasons it's good to have loops in wiring systems is that, well, it gives freedom of movement. If you have moving joints, things don't tighten up too much, but there are other reasons as well. On my spacecraft, if you have good eyesight, you can see a little blue and red wire on halfway around the loop on my spacecraft, and it's an intermediate connection. I have a little wire for a temperature sensor and a proximity sensor. And interestingly, on our laryngeal, recurrent laryngeal nerve, we also have two intermediate connections, one to the esophagus, one to the trachea, remarkably similar to my system on a spacecraft. And those tiny nerves can't go on their own. They need to piggyback another nerve cells, and that's exactly what happens in the human laryngeal nerve. But then there's even a third reason for having a loop, and that is when you're assembling the system in the first place. For my technicians to assemble my wiring system, you have to have slack and loops. In the case of a human being, when a baby grows in the womb, organs are moving apart, and you have to have a degree of slack in the wiring system. So seeing a loop in the wiring system is exactly what you would expect if God had designed it. And yet Richard Dawkins writes in his books that this isn't what you'd expect from a designer, but he doesn't actually know how design works himself. So the human body has 150,000 kilometers of brilliant wiring. It's one of the most awesome examples of design and planning in creation. I find it interesting that people like Dawkins attack what is the most overwhelmingly obviously designed system. Just to mention that I haven't gone into detail on the micro design of the nervous system, just to mention very briefly, you have connections in the human body. In fact, our brain contains trillions of connections, these synapses, and you might think, well, surely an individual connection, a synapse, is simple, but it's not simple at all. Each synapse contains hundreds of complicated proteins in order to get signal transmission, which is very complicated because down a neuron you have electrical impulses, but at connections it translates to a chemical transfer signal and then back to an electrical signal. So just one connection is immensely sophisticated and complicated. And when you think the nervous system grows from a tiny cell as the human body grows in the womb, you just cannot comprehend how this is possible, that this could form. If you're holding a baby, you probably think this is a very beautiful baby, but I'm thinking, hang on, there are 50,000 neurons being formed every second in this baby. Quite an incredible thing. My best technician can make about 3 connections a second, which is in a completely different league. It's just incredible what goes on as a baby grows in the womb. And our brains are just unique. We have trillions of connections in our brain, 1 billion connections in just 1 cubic millimeters. The storage capacity in our brains is about 1 million gigabytes. That's about 1 million memory sticks. And we have 100,000 miles of blood vessels in our brain, not just to feed our brain, but to cool it as well. One of the reasons it's difficult to make supercomputers that are small is that it's hard to keep them cool, but our brain has a wonderful way of doing that. So how does the human brain compare with a supercomputer? A couple of years ago, IBM broke the world record for a powerful supercomputer, and it's about the size of this hall, actually. It's called the Summit supercomputer? Well, the Summit supercomputer by IBM, it's very powerful, 0.2 billion calculations per second, but that is only a fifth of one human brain. So the best supercomputer in the world would fit into this building, and it is less powerful than one human brain. And look at the electrical power needed, or chemical power needed, to run those two systems. It needs around 13 megawatts to run the supercomputer, but your brain needs a mere 20 watts. That's almost a millionth of the IBM supercomputer, which is less powerful than your brain. So that's an interesting comparison, isn't it? Your brain is an amazing thing. So we are fearfully and wonderfully made, just like the Bible says. God makes it look simple. From the outside, the human body looks simple, but on the inside, it's absolutely not simple. God does things we cannot comprehend, and the nervous system is surely a brilliant example of that, because you have your blood circulation system, the digestive system, the skeletal system, all integrated perfectly with the nervous system. God is in the detail. Sometimes you hear people say the devil's in the detail. A better expression is God is in the detail. There are incredible details in the human body, and God has been in every single one. It shows his care and attention. I mentioned the verse, fearfully and wonderfully made. I like the version, fearfully and wonderfully wired.